Okay, well, this took me way longer to decide what I needed to do with this 3.4 than I feel it should have. But then, of course, you know, every answer is easy once you know it. So I guess that's kind of what happened here. So they want you to extend example 3.5 by showing that this particular map maps any circle passing through -1 to a line. And I was kind of going from first principles and so forth as far as just this mapping here. And finally, after quite some time, I realized that really they just want us to pretty much use 3.5, I think. Certainly that's a nice way to go. So let's go let's go there and back up a little bit. There we go. And so this was the proof of theorem 3.4, and let's see, yeah, there's the example 3.5, and you know, I was trying to do it this way, and I just I was having a tough time. I don't know, I'm, you know, I can get pretty far with it, but it just never seemed like I quite got to where I needed to. But now, you know, really, if you look at the proof of theorem 3.4 and go back here to the theorem 3.4, this is, I think, really how to go. So so we have our map here. I'm gonna kind of switch around. Let me write something down as I say it here, and then I'll switch to where you can see that that's what I've written down. You know, so I've got I'm looking at that top line there, f of z equals BC minus AD over C squared times 1 over Z plus D over C, and then plus A over C. And our particular map is f of Z there is Z minus 1 over IZ plus I. And so now let's switch to here. So I wrote those things down, and so, you know, we see that A equals 1, B equals -1, C equals I, and D equals I. And so now, if I want to write my f of z in this form up here, we have f of z equals, so BC, so that's -I, minus AD, so minus I, so that's a -2I over I squared. So we get a 2I is what we get out there in front. And then C over D is 1, and so this is times 1 over Z plus 1. And then A over C is 1 over I, which is the same thing as minus I. Okay, so now what I want to do is concentrate on this 1 over Z plus 1, and the idea would be that if 1 over z plus 1 for what we need goes to a line, then just multiplying by a constant or subtracting a constant are going to still send us to a line. Okay, so that's where we are with that. Let me go back to the text. And so, you know, trying to go this route in here just really wasn't doing much for me. However, if we look at the proof of theorem 3.4, what they want to do is they want to show that 1 over z, or that inversion, goes to either a circle or a line. Okay, so if we look at this function 1 over z, and then we take a circle in a particular format. Now, and this is kind of the key here. So we have that we're going to use z such that, and what I want to do is, instead of going through -1, I want to look at z that go through the origin, so circles like that, you know. So the circle might look something like this, where that's our z0, and then it goes through the origin like that. Whoops, I need to show you that picture, I guess. So come back here. So we want z that looks something, you know, is on this circle here, and so we see the radius is just the magnitude of z0. Okay, so let's look back here. So what I'm going to do is write this thing down here. So we'll have x minus x0 squared for that circle, plus y minus y0 squared, and then that's going to equal x0 squared plus y0 squared, because that would be the magnitude squared. Okay, so we'll do that, and we'll actually explicitly look at these constants, alpha, beta, gamma, and delta here. And so let's go back here. So I have that my z would be x minus x0 squared plus y minus y0 squared equals x0 squared plus y0 squared. Now if I multiply this out, I'll get my x squared. I'll get a minus 2x0x, and then I'll get a y squared, and minus 2y0y, and that equals 0, because what happened, we got a positive x squared and a positive y0 squared. I subtracted those from both sides, and so we get this, and rewriting it this way, x squared plus y squared, y squared, and then I'm going to go with plus a negative 2x0 x, and plus a negative 2y0 y equals 0. Okay, so we have that, and so from that other page we had alpha times that x squared plus y squared. So alpha is equal to 1, beta is equal to negative 2x0, gamma is equal to negative 2y0, and most importantly, delta equals 0 in this case. All right, so looking back here, right, 3.1 said we could write in this format, and our alpha was 1, our beta was a negative 2x0, our gamma was a negative 2y0, but delta was 0. Now if we kind of just jump down to the bottom line of this proof, it said that if we look at the map 1 over z, okay, so 1 over z, what we found was that, so for 1 over z in general, right, we found that we would get, according to this, alpha plus beta times u minus gamma times v, and then the delta. But delta is 0. So if I come back here, it said our image. How did they write that image? Oh, they just set it equal to 0. Okay. So for 1 over z, in this case, then 0 is equal to 1. And then it was beta times u, so minus 2x naught times u, and then plus, because that was a negative, 2y naught times v. But then delta was 0, so we get this. But then you see, oh, that's a line. Okay, so that says that 1 over z sends all circles containing the origin to lines. Okay, because we don't have the u squared v squared part in there. Right, so that's just a straight line. So that's the 1 over z. Oh, okay. But now notice if we have 1 over z plus 1, okay, and let w equal z plus 1, that gives us 1 over w, okay, which in turn sends 0, 0. Well, doesn't send just the point, I guess, to the line, but it sends, and boy, that's a good question. Oh, well, sends. It really sends it. Yeah. So try that again. Okay, it sends circles through the origin. So we just said this, to lines. Okay. So if w, so what that means is that circle would cause w to be at 0, 0. But if w is equal to 0 plus 0i, then z, which would be w minus 1, would be negative 1 plus 0i. And so what this says is if well, not if, I guess, we'll say thus, 1 over z plus 1 sends circles containing -1 plus 0i, 2 lines. And that is how we do it. It's just a simple substitution from the proof of 1 over z. So the 1 over z, that if we go through 0, 0, it will drop delta off. It'll make delta 0, so we get this, so that's a line. And so if 1 over z does that for 0, 0, then 1 over z plus 1 will do the exact same thing for any circles going through what do I want to say here? -1, 0. And actually, more generally, 1 over z plus any constant, so I don't know, we'll call it c since it's in the complex variables, sends circles containing z equals c, minus c. Try that again. Oops. Minus c, 2 lines. And in general, what we have again is that you have some az plus b over cz plus d, and so you factor out the c and so forth, and look at it this way. This you end up with this thing. Where that particular c is actually d over c. Okay, so in this more general Mobius transformation formulation, this should sends circles containing minus d over c, 2 lines. So there you go. There is 3.4, very generalized 3.4, and yeah, it took me a long time to get to this. I just sort of feel like I personally feel like I was sort of led astray by just kind of how the book suggested it. Now, I only say led astray in that I was trying to set it up just like they had set up example 3.5, and I just could not get things to work very well that way. So but then when I realized that the proof for the 1 over z could be utilized, because then we can always send things back to where they're at the origin through a translation. That's when I realized that you could do this in a much simpler fashion, as just kind of using the fact that we knew what 1 over z did, and so in our case it's this minus d over c. Well, this was iz plus I on the bottom, and so minus d over c was equal to minus I over I, which is negative 1. And so those went to a line. So that sounds good. All right, we're done with that one, I think.